All right, guys, welcome. We are going to continue our discussion in the CCIE mentorship program with EIGRP. We've covered the classic EIGRP configuration. We also covered EIGRP named mode. So the next topic that we're going to do for today is the metric configuration. Now, this is a little bit of going to be a little bit of review from what we saw with the classic configuration as well as named mode configuration. In addition, we're going to see more of this when we get into traffic engineering and unequal cost load balancing. So there's going to be a little bit of repeat between these topics, but you know, it doesn't hurt to kind of see things more than one time. So we're going to take a look at that today. I was hoping to get to the wide metrics today as well, but unfortunately we're going to have to just do the classic metric configuration today, and then hopefully in our next session, which will either be Tuesday or Wednesday, we can do both the traffic engineering and the wide metrics session together. All right, so that's what we're looking at covering today. And I've got a basic topology here. I'll put this, I didn't get a chance to put this topology into the Google Drive. However, it's very similar to the topology that we had before. So I would say that we could probably use the same topology that we loaded the last time. Let me just make sure real quick. We've got our configurations loaded on our two routers here. And we're going to do kind of a quick review, investigation of the configuration of these routers, and then we'll take a look at metric manipulation and talk about how we can verify metric calculations, how we could potentially even manipulate some of these metric calculations, and so on. Like I said, we're probably going to see a little bit of redundancy from what we saw before. Show IP EIGRP neighbors. All right, so it looks like we've got, let me see if I have IP addresses at least. All right, so we got IP addresses, but we don't have EIGRP running in this particular topology as of right now. Okay, so let's go ahead and take a look at our base configuration. This is the topology that we're going to be using throughout the day to kind of talk about the classic metric calculation, and we'll talk about how we can manipulate some of the different values that are part of the metric. You know, we talked a little bit about this the last time, how EIGRP uses essentially the minimum bandwidth along the path towards a destination network and the total delay by default to compute the overall routing metric. We can configure other metrics, but Cisco actually does not recommend using the other variables within the calculation. For example, they don't recommend that you use the load and reliability mechanisms that can be included as part of the metric. All right. So we are going to focus our attention on the primary concepts of the metric, which is essentially the bandwidth and the delay. But we're going to talk about how we can kind of manipulate that. One of the concepts, because we did cover a lot of this in the last lesson, one of the concepts that I wanted to walk you guys through was maybe manipulating some of these values. And we'll see that again when we get into traffic engineering, the traffic engineering discussion a little bit later on. All right. So the bandwidth and delay metrics, that's what we're essentially going to use to determine the overall path metric. And we'll use this topology to kind of go through the process. And then that's it. We'll just take a look at how we can manipulate these values. It's entirely possible that in either the troubleshooting section of the CCIE or the configuration section of the CCIE that they would make you identify potentially why there would be issues for traffic taking the wrong path or not utilizing the correct path in the process of routing. All right, so we're going to take a look at that. We'll take a look at the topology database. We'll take a look at individual routes. We'll take a look at the different K values, and the idea that the K values have to be adjacent, or they have to be common between adjacent routers, which means essentially they have to be common throughout the entire topology. Right? We'll talk about K1 versus K2, K3, K4, and K5. We'll talk about the whole concept of no floating point math. So how do we do our calculations if we have incomplete values or values that don't round to or calculate to whole numbers, stuff like that. All right. So let's go ahead and get started. This is mostly going to be a demonstration, and then perhaps manipulations, and we'll talk about what the effect is of changing metrics at certain points within the network. That's a very important concept. In fact, let me get a snip of this topology here. And because I want to use this diagram here to kind of demonstrate some of the concepts. So let me put that into Paint here. And we'll use this diagram to demonstrate some of the concepts that we'll be talking about throughout the configuration. So let's go into HQ, Show IP Protocols. We are running EIGRP 100. Show IP EIGRP interface. So it looks like we are running EIGRP on all of our interfaces: Ethernet 1.0, Ethernet 1.1, Serial 2.0, Loopback 0. So we're good to go there. But you can see we really don't have any peers running on this particular network. So what I'd like to do is I'd like to do an incremental implementation of EIGRP by starting and configuring EIGRP on the serial interface, and then taking a look at the path metrics and identifying the specifics about that metric. So let's go ahead and go into our branch router and config T, router EIGRP 100. We're going to do this in classic mode this time because we will be doing our EIGRP configuration in we'll be doing our EIGRP configuration in named mode next time when we want to talk about the wide metrics and how wide metrics are calculated. So let's go ahead and enable EIGRP on the serial 2.0 interface, 172.16.3.2, 0.0.0.0, and I should get an adjacency in this case. Yep, and let's go ahead and also enable it on the loopback, 192.168.1.0. So we can advertise that network. So I've got an adjacency. If I do a show IP EIGRP interface, I can see that on serial 2.0, I've established a peering relationship with that particular peer. So if I do a show IP EIGRP neighbors, I have a neighbor listed there. We've already gotten information about 3 different networks. If we look at the topology here, that kind of makes sense, right? Because the HQ router has got these loopback interfaces, and it's got these other networks here, the WAN link interfaces. Now, from the branch router perspective, the only networks that I'm going to add to my EIGRP routing process are going to be the loopback interfaces, because these are all connected interfaces. Plus, we're not running EIGRP on these 2 serial interfaces here, or Ethernet interfaces, excuse me. Ethernet 1.0 is not running EIGRP presently, and Ethernet 1.1 is not running EIGRP presently. Okay, so let's take a look at what the routing table looks like from BR's perspective, and then start to do some calculations. So if I do a show IP route, I can see that I do have a route here, EIGRP route, 192.168.0.0. That's interesting. Seems like I'm missing the 209. Let me go to the HQ router and see if 209 is even part of EIGRP. Show IP interface brief. Let's do this. Show IP interface brief, exclude down. Okay. So 209 is loopback 1, show run pipe section EIGRP. And I'm guessing that the 209 network is not being advertised. That's okay. We could certainly advertise it, but really it doesn't matter in this particular case because the loopback route is going to look pretty much the same as that. The loopback 0 route is going to look pretty much the same as the loopback 1 route. So let's do a show IP route, 192.168.0.0. And we can see from this particular route, we're learning this through EIGRP 100. It's got a metric of 229.7856. It's an internal route. It's coming in via EIGRP 100. 3.1 is the next hop. The exit interface is serial 20. We learned about this route 2 minutes and 32 seconds ago. And we can see all of the individual pieces that are used to calculate this metric. Total delay is 25,000 microseconds. Minimum bandwidth along the path is 1.544 megabits per second. Reliability is 255, which is the highest level of reliability. MTU is 1500 bytes, and the loading is 1, which is the lowest level of loading that you can have with an EIGRP metric. So several different things that we want to take into account here, but let's first of all take a look at how this metric is calculated. So let me pull up real quick here so I can put this in the diagram and we can reference this. EIGRP metric calculation. And we will see, hopefully I'll be able to find a pretty decent picture here because we were looking at this the last time. The overall metric calculation, there's several K values that are involved, but let me see if I can find a nice clean picture of, yeah, there we go. That'll work perfectly. Okay, so I'm going to copy this image so that we can paste this into our document here. Well, that's not going to work. Here, let's just, I'll just put this up here on the right-hand side. Yeah, it's okay. We don't need that. I'll just put it right up here. Okay. So there is our metric for EIGRP. The metric is equal to K1 times the bandwidth, and we've got a little indication of min, plus K2 times the bandwidth, divided by 256 minus the load, plus K3 times delay. Now, the only thing that they're missing here is how is delay calculated, right? And if you guys recall from our last discussion, delay is equal to, let's change the font there so it's easier to read. Oops. Okay, so delay is going to be equal to the sum of all interface delays along the path in tens of microseconds. Now, keep in mind that we're talking about classic mode, not named mode or at multi-address family mode. All right, we're talking about the classic configuration. So these are the elements of the metric calculation. Now, remember, I said, first of all, there is no floating point math in the calculations. I'll explain what that means in a minute here. Also, only egress interface values are used in the calculations. All right, let's see, I saw a chat message here. Let me see what it says. I can talk about K6. K6 does not exist in classic mode configuration. K6 only exists in named mode configuration. So we will be talking about that in our next lesson when we get into the discussion of wide metrics and named mode configuration. Ryan asks, in terms of the exam, should the local direct connected interface be advertised via redistribute direct connected or enable EIGRP in the interface? It really depends in this case on they might actually give you a specific requirement that states that you have to redistribute connected routes, or they may talk about a scenario where you have to run EIGRP on certain interfaces and run OSPF on other interfaces and then do redistribution between the two protocols. It's hard to say specifically what they're going to request you to do with regard to the actual configuration. Okay. They might even ask you to redistribute routes, connected routes or static, or another routes from another routing process, and then apply some sort of filtering or route maps to that, or prefix lists or whatever it might be, to that redistribution process. So it's really totally up in the air as to what they're going to ask you to do. I remember one of my exams back in the day when it was version 4, they said that I needed to redistribute RIP into EIGRP, but I could only redistribute like the first subnet, the fourth subnet, the seventh subnet, or whatever. And so what they were asking me in that particular case was, and they said I could only use a single line access list or a 2-line access list. I can't remember the specifics, but essentially in that particular case, it was a basic redistribution problem, but they wanted me to be able to calculate a bitwise mask. Some sort of access list mask that was going to match specific routes, and I could only do it in a certain way. So it's really hard to say specifically what they're going to ask. Obviously, we're going to talk about redistribution. We're going to talk about, we already did talk a little bit about, route maps and that, but we'll talk about other traffic engineering concepts when we get into each of the different protocols. So it just depends, right? We're going to take a look at just doing the configuration completely in this topology and focus our attention primarily on, just making sure that we have full convergence and that we have a complete understanding of how the paths are selected based on the metric calculation. Okay? So the metric weights, default K values, are going to be K1 and K3 are going to be equal to 1. And K2, K4, and K5 are going to be equal to 0. K1 is going to be, obviously from the formula here, is going to be related to bandwidth. K2 is going to be related to load. K4, well, we'll do them in order. K3 is going to be related to the delay. And K4 is going to be related to, in this case, reliability. And then, even though it's not really listed here, and actually K5, the metric is not really, the MTU is not really part of an EIGRP metric, oftentimes you will see K5 related to the MTU, even though it's not really technically part of the metric. So I'd put a little asterisk there, because that's not necessarily entirely true. Certainly K5 could also be related to reliability, because that's the part of the formula that it's being applied to. So you would change these K values if you wanted certain components of the metric to matter more than others. The K values end up being multipliers against a component of the metric. Right? So if I wanted, for example, only delay to be counted as part of the metric, then I would simply make K1 a 0. If I wanted the bandwidth to take more precedence over K2 or K3, then I would change the K1 value to a higher value. We'll talk about what some of the values we can set are. Now, Ken did mention a K6. In the case of a classic EIGRP configuration, there is no such thing as K6, but we will definitely talk about K6 in our next lesson when we get into our named configuration. All right. So those are our default K values. There's no floating point math in our metric calculations. Only the egress interfaces are used in the calculations, and all of the values that are used for the metric calculation can be viewed using the show interface command. Okay, and we'll take a look at that. So if I was to look at from the perspective of the branch router here, all right, let's go back to our branch router. And I did a show IP route, EIGRP. We can see the 192.168.0.0 route has a metric of, from the branch's perspective, of 2298.2297.856. All right. So if I go back to my diagram here, I can put this value in for the 192.168.0.0 subnet. All right. So we know that we're only learning about this network presently from our serial 20 interface. So we want to be able to find out how is that metric being calculated, how can I influence that metric, and so on. All right. So the first step in understanding this process is to understand what interfaces are being used to calculate that particular metric. And if I'm going in this direction, which is what we're referencing in this particular case, only that interface and that interface is going to be used in the metric calculation for that particular path. And by the way, the metrics could be altered or changed in both directions. So you might have one metric in one direction, you might actually have a different metric in a different direction, depending on where you're manipulating the values. So if I go into my branch router and I do a show interface, serial 20, I can capture the two values that are used by default in the metric calculation, and I can place those numbers on my diagram. All right. So let's go ahead and do that. We've got the bandwidth there of 1544 kilobits per second and a delay of 20,000 microseconds. I'll do the same thing on the HQ router, and in this case on the HQ router, show interface loopback 0, I'll grab the values from the HQ router here. And now that I know the values of each of these interfaces, I can now place the values into the formula and calculate this overall path metric for that particular flow in that direction. All right. So if we look at the formula here, bandwidth is 10 to the power of 7 divided by the least bandwidth along the path, and this is really important, in kilobits per second. Okay. So we're talking about the least bandwidth along the path in kilobits per second, not megabits per second. In OSPF, we use megabits per second. So I think it's pretty clear that the serial interface on the right is going to have the slowest bandwidth because the bandwidth of the loopback is much, much higher. So if I go ahead and put this value into the formula, 10 to the power of 7 divided by 1544, oops, clear, 1544, oops, what the heck? 10 to the power of 7 divided by 1544 equals 6476. Remember, there's no floating point math, so we need to drop the remainder here. So from the perspective of the metric here, the bandwidth calculation is equal to 6476. All right. Now we do have to multiply that whole thing by 256, but let's go ahead and calculate our delay. The delay is the sum of all the interface delays along the path in tens of microseconds. You'll notice here that the delay is actually listed in microseconds, which means that the delay is going to be 20,000 microseconds plus 5,000 microseconds divided by 10, because it has to be in tens of microseconds. So we're going to have a delay of 2,500. You guys agree with that? 20,000 plus 5,000 is 25,000 microseconds. All right. 25,000 microseconds, and then we divide that by 10 is 2,500 microseconds. So now we simply just add those numbers together, because again in our formula, because the default value of K2 is 0, that goes away. And because K4 and K5 are not used, that goes away. So we don't multiply here, we just simply drop that part of the formula. Our formula ends up being 1 times the bandwidth, 1 times the delay, times 256. So if I take 6476, and I add 2,500, and I multiply that times 256, I get 2297856. Simple enough, right? As long as you follow the basic rules, you're going to get the right calculation every single time. So one might ask then, and we're going to see more about this when we get into the traffic engineering section, one might ask then, well, how do I influence that path metric, right? Well, if you go into an interface, because, let's go into our branch interface, because the metric is calculated based on bandwidth and delay, I could either change the bandwidth, and I can change that in kilobits per second. This is what would affect the metric calculation. Notice, though, that it does have a limited size. And that's the issue that we have with classic EIGRP configuration, is that the bandwidth can only go up to a certain speed. And if you start to get beyond that speed, then those links start looking the same. Now, back in the day, this was okay because we didn't have interfaces that had that kind of speed, right? This is 1 megasecond. This is 1 gig. This is 10 gigs. This is a terabit, right? So we've got 1, 2, 3, 4, 5, 6 zeros there. 1, 2, 3, 4, 5, 6, 7. So we can go up to 10 terabits for a particular, the speed of an interface. But now we're going to start to see interfaces that have much, much faster speeds. And the other thing to keep in mind is how large is the actual field in the actual update or the advertisement. We'll talk more about that when we get into the wide metric calculations in our next lesson. We're going to spend some time going through that and talking about what the limitations of the classic metrics are. All right. So if I go into interface serial 20, I can change the bandwidth of the interface, which will affect other things as well, right? It'll affect QoS calculations. It will affect, quality of service operations. It'll affect anything that really utilizes that bandwidth value to make a calculation. See, with OSPF, we had this IP OSPF cost command that we could run, which would allow us to set the cost of the interface without affecting anything else in that system. Unfortunately, with the EIGRP, we don't really have that benefit. We can't just statically configure the metric on the interface. I can change the delay value as well, but let me show you something here. It's kind of annoying. Actually, this is probably more appropriate, right? Because the metric in the formula is in tens of microseconds, and when you set the delay on an interface, it's also in tens of microseconds. All right. Well, that's a good thing, but when you go do a show interface, the output shows in microseconds. So it can be a little bit confusing moving back and forth between these various formats of the metric, but we can set the delay on the interface. I'm not going to modify anything right now because I do want to talk about what the effect of setting these values is on the feasible distance, but also what the value of what the impact of setting these values is on the reported distance. Really, really important concept. We'll take a look at that as part of our discussion here. So because of the way the metric is calculated, if I was sourcing traffic from this interface and then sending traffic over to this interface, the metric utilizes these interfaces for that calculation. But on the return path, we're going to be using this interface and this interface for the return path. So the metric does not necessarily have to match or may not match in both directions. All right, let me clean some of this up here. All right, so that's another consideration to keep in mind, and I'm going to show you how that could, how we could be affected by that in a little bit. Kilobits per second, I'll put that back on there. Okay, so let's go ahead and enable our next interface, which I guess I'll go ahead and enable Ethernet 1.0 on the branch router for EIGRP. So router EIGRP 100, do show IP interface brief, exclude admin. So we're going to do a network of 172.16.1.2, 0.0.0.0. So I should get another adjacency here. Now I've formed an adjacency on the top link and the bottom link. And if I do a show IP route, I can see that my path has changed and my metric has changed. All right, makes sense, right? If I do a show interface Ethernet 1.0, the delay has gone down, so we lost about 19,000 microseconds in delay, and also the minimum bandwidth along the path has gone up to about 10,000 kilobits per second as opposed to 1.544 megabits per second. So if I just do the quick calculation here, I've got, let's see, 10 to the power of 7 divided by 10,000. So that's equal to 1,000, and then I'm going to add that to that 510, and then I'll multiply that. Oops, I didn't do that right. Let me try that again. So 10 to the power of, well, that's 1,000. We already know that. All right. Make sure I did that right. 10 to the power of 7 divided by 10. 1, 2, 3. Okay, so that's the bandwidth calculation. The delay is the sum of the delays oh, that's what I did wrong. It should be 600. So we've got 600 plus 1,000 times 256. So there's our metric, 409,600. All right, makes sense. Because I've got a delay of 6,000 microseconds divided by 10 is 600, plus the 1,000 is 1,600 times 256 is 409,600. So the top path becomes more preferred than the bottom path. If I do a show IP EIGRP topology, we can see that both paths are listed in the topology database. This is the original path over serial 2.0, and this is the path that goes over Ethernet 1.0. Okay. Now there's a couple things that I could do here. One of the options that I have to maybe even be able to use both paths is to set up a variance option and use variance to do unequal cost load balancing. And when we get into the traffic engineering discussion, we have that right here. Traffic engineering and unequal cost load balancing, we'll spend quite a bit of time talking about that. We're going to get into the specifics of what kind of load balancing EIGRP does and how does it decide what what interfaces to include and what interfaces get excluded and so on. Now you'll notice the second number in this database here, 128.256 and 128.256, that second number in the database is what we call the reported distance. That is the cost for my neighbor to reach the same destination. All right, so if I did the math, let's go to our HQ router here, show interface loopback 0, and I go ahead and I do the math. Where's my calculator? There we go. All right, so I've got 10 to the power of 7 divided by 8, 1, 2, 3, 4, 5, 6. So it looks like I've got a cost of, or a calculation of 1, if you will, for the bandwidth. Because again, I don't round up, I round down, I drop the remainder. And the delay is 500 microseconds, or 5,000 microseconds. So if I take 500 plus 1, of course, multiply that times 256, we get 128.256. So that is the local cost for this interface. Now I would have been able to see that by just doing a show IP EIGRP topology and looking at the connected loopback interface right here. Feasible distance is 128.256. Even though it is a connected route, it is still running EIGRP, which means it's still going to show up in my EIGRP topology database. All right. So if I were to walk through a scenario here, and I'd say, okay, to go from the branch router to this loopback, I want to take the Ethernet link. But to go from the HQ router back to this loopback, I want to take the serial link. Not that you'd ever really want to do that in the real world, but you know, it's part of maybe us identifying how we can manipulate these metric values to be able to force one path over the other. Now you could certainly do it with policy-based routing or maybe static routes or something like that, but I want to manipulate metric values to make the serial link appear more preferred over that top WAN link, but only for the return traffic. Which means if I look at my topology diagram, on the egress side, if I'm going this way, right, to get to that network, it's this interface here and this interface here that would affect that path metric. But if I want to say, let's go ahead and send the traffic back this way, then it's going to be this interface and this interface. All right, because again, only the egress interface matters. And this applies, by the way, to OSPF as well. All right, not necessarily RIP, because RIP uses hop count as a metric, but and BGP uses path vector attributes. So in both of those cases, it's not going to use the same kind of concepts that we're talking about here. All right. So we already know that the top path is going to be preferred to go back over to the HQ router. So what could I do to make the bottom path more preferred? Now there's two places I could change values to make the bottom path more preferred on the return. All right. Here's the issue that you have though. I can't change the loopback interface because the loopback interface is going to be part of any route that's being advertised from the branch router over all three circuits. So I could make this interface look worse, or I could make this interface look better. It's totally up to you. Now you could also do this on a per route basis. When we get into the traffic engineering section, I'll talk about how to manipulate some of these values per route and how we can do traffic engineering by using offsets and different kinds of things. I think we even saw a couple of offsets when we were playing around with this the last time. So if you think about what I have to do to manipulate these paths, you have to say, okay, well, I know that the delay on this interface is 20,000. All right. And if I go into my HQ router, the delay on Ethernet interface is 1,000. So I already kind of know what I'm dealing with from the perspective of delay. Bandwidth also is a factor. We've got 1544 here, and we've got 10,000 there, right? If you go back to your HQ, you can see that the bandwidth is 10,000 kilobits per second. So if I wanted to, I could simply come into interface Ethernet 10, and as long as I change the bandwidth to something less, notice the bandwidth is in kilobits per second. So if I change it to something less than the serial link, and I change the delay, which is in tens of microseconds, by the way, to something higher, then that path should no longer be preferred. Remember, I'm setting the best I can do on adjusting the delay is in tens of microseconds, because the formula is in tens of, or the input data is in tens of microseconds. So by putting a delay of 2001, I'm actually setting a delay of 20,010. Okay? So if I do a show IP route, I can actually see here that this EIGRP route is now preferring the serial link to go back to that loopback. So if I do a trace route to 192.168.1.1 source, let me get my diagram here, 192.168.0.1 most likely. All right, I think it's 1.1. Let me make sure. Show IP interface brief. It is 1.1. Okay. So I sent the packet over 3.2. Now if I do the same thing on the branch router, trace route 192.168.0.1, source 192.168.1.1, I should see that I'm actually using the 172.16.1 subnet to reach that destination, and we were using the 3 subnet to get back. All right, to go back from HQ to the branch router. All right, and sure enough, we're using 1.1 to reach that destination. So we've got an asymmetric routing scenario here just by manipulating some of the path attributes. Now, I don't necessarily have to manipulate both, right? I could, for example, just manipulate delay, but it was just easier for me to say, look, I'm just going to make them both worse, and then I know that path is not going to be selected on the return. So the traffic is going over this way to get there, and then it's coming back this way to go back, just by simply manipulating those interface metrics. What's some of the considerations that we have to take into account when we're dealing with this, though? Some of the considerations you take into account are obviously asymmetric routing. From a security perspective, is not really the optimal choice because oftentimes we might have security policies in place that are stateful. In other words, we have some sort of stateful inspection that's going on, or we have policies that are applied to one interface but may not be applied to another interface that may or may not work. All right. Based on the fact that the packet is traversing a different link on the return or whatever it might be. Okay. So again, not something that we typically would do, but right now I'm just kind of showing you how to manipulate the metric and how to review what's happening with that particular path. All right. Now there is another thing that I definitely want to show you guys that I think is extremely important, and that is the concept of manipulating these metrics while still maintaining a feasible successor. So I'm going to go ahead and enable EIGRP. Let me first of all clean up HQ because I don't want show run interface Ethernet 1.0. I don't want that asymmetric routing. So I'm going to do no bandwidth and no delay. That'll take out those values, and we should be seeing now that we're going over the Ethernet link. Yep. So we've got symmetric routing back into place here. Okay. So I'm going to go into the branch router, and let's go ahead and enable EIGRP network 172.16.2.2 0.0.0.0, and I should get another adjacency. All right. So now if I do a show EIGRP neighbor, I can see that I have, well, it's technically, I guess, described as 3 neighbors, but it's not really 3 neighbors. It's the same neighbor over 3 different interfaces. And in fact, if I do a show IP route, you can see that I'm now load balancing or load sharing over those 2 links. Again, maybe that's not my objective. Maybe my objective is to only utilize one link and use another link as a backup. So if I wanted to say use the 1.1 link as a primary, use the 2.1 link as a backup, then I can manipulate either of these 2 interfaces, either making one look better or one look worse to influence which path that traffic is going to take. Given the fact that it's only the egress interfaces that are going to be used to do this particular calculation, you need to make sure that you manipulate these paths symmetrically if your goal is to provide for symmetric routing. So if I want to use, say, this path for the traffic going back and forth, and this is my backup path, and this is my tertiary path, then I want to make sure that I manipulate, maybe make this bandwidth a little bit better, or make the delay a little bit less, or whatever. In fact, let's go ahead and do that. So if I go into Ethernet 1.0 on each router, I'm just going to set the delay to a little bit lower. Interface Ethernet 1.0. And so instead of a delay of 10,000 microseconds, let's do 910. Let's do 990. Okay. So go away. Show interface Ethernet 1.0. You can see now the delay is 990 microseconds. And if you look at this interface, show interface Ethernet 1.0, you can see the delay here is 1,000 microseconds. So in order to provide for symmetry, interface Ethernet 1.0, delay 99, show interface Ethernet 1.0. So now our delay is 990 microseconds. Show IP route EIGRP. We can see that we're only using the 1.2 path, which is the top path. If I do a show IP EIGRP topology, I can see that this metric here is slightly better than this metric here. Okay, so this is now my successor. This is my feasible successor. And then this is another route candidate because it does meet the feasibility condition. Remember, for a route to be viable, the reported distance of that path, the reported distance of this path needs to be less than the feasible distance of the best path. 128.256 is lower than 409.344. All right? Really important concept. In fact, let's create an offset list. I'll just do it on the branch side. Oh, actually, you know what? Let me do one more thing. I wanted to show you. Let me do a no delay here, just to show you what happens. So if I do a show IP route EIGRP, oops, I'll do it on the other router first. All right, show IP route EIGRP. You can see that we're not load balancing to that particular destination. We just have a single route to the 1.0 subnet. But if I go into the branch router, show IP route EIGRP, you can see that I'm load balancing back to this subnet. Because from the perspective of branch 1, these two interfaces look the same. So when I'm going from the right to the left, I'm going to load balance to reach the left destination. I'm going to use both paths to get here. Okay? But on the return, I'm only going to use the top path to go back. And that's because the metric or the delay was changed on that interface locally. So that's another concept that's important to understand, is that these values are locally significant. How we're manipulating these values are locally significant to the router. So whenever you're changing metrics, and this applies to OSPF as well with regard to cost, whenever you're changing metrics for a particular path, you need to make sure that you're manipulating the metrics in a way that you get predictable behavior. Okay? Very, very important. Now let's say I just want a delay to be the only part of my calculation. Actually, let me do this first. Let me do a show IP protocols. And you can see from the show IP protocols output what the default metric weights are for EIGRP. K1 is a 1, K2 is a 0, K3 is a 1, K4 is a 0, K5 is a 0. Notice there's no K6 in this particular case because we're not using wide metrics. If I go into router EIGRP 100 and I use the metric weights command, I can modify these values. All right. Never understood this. I'm sure there's a reason for it, but the type of service is always set to 0. So then I get a K1 value. Notice this is an 8-bit field, so it's just simply a multiplier. So K1 I could say equals 0, K2 equals 0, K3 equals 1, K4 equals 0, and then finally K5 equals 0. Now when I do this, I'm going to lose my adjacency because metric weights are advertised in the hello packet. In fact, if I come back to my topology here and I start capturing data on this interface, you will see that the metric weights are being advertised in the hello packet. So we've lost our adjacency because we don't have common metric weights configured between the routers. Now Cisco recommends that you never change these values, and you are not going to be required to change these values on the exam for that reason. Cisco really does not want you to change the K values. So we can see from our hello message here, we have autonomous system number, and then under the parameters section is where we see all of our K values. So this is what I received from my peer router. K1 and K3 are turned on, and of course if I looked at what I was sending to the peer, I would see the opposite. Well, not the opposite, but K1 would not be active. All right. Go back to our parameters. And that's interesting. I would not have expected to see that. That is really interesting. All 255s. This...
It says peer termination, so maybe it's just saying that, you know, since there's no match.
Right, so it's, I'm surprised that it would put these values in there, but maybe it's just overriding these values like almost like a poisoning of the K values, so that we're identifying to the other peer that we're going to go ahead and terminate the connection. Let's see what the expert info says here. Probably not much, but let's see. Yeah, it's just, this is Wireshark. Anything in brackets is being added by Wireshark. It's not actually part of the payload. We should be able to see at some point the actual K values. There we go. So this is a normal hello packet indicating that K1 is 0 and K3 is 1. All right, no big deal. We just simply go into our HQ router and go into config T, router EIGRP 100, metric weights 0, 0, 0, 1, 0, 0. Oops, 0. So K1 and K2 are off, K3 is on, K4 and K5, oops, I thought I had enough zeros, I just don't have the weights in there. All right, oh. Metric weights 0, 0, 1, 0, come on, stop it. 0, 0, 0, 1, 0, 0. There we go. So now we should get our adjacencies back. Yep, all our adjacencies came back. Now if I do a show IP route 192.168.0.0, 0.1, or 1.0, sorry, we can see that the metric here is only 153344. We're still reporting on the delay and the minimum bandwidth, but only the delay is being used in the calculation. Show IP protocols will demonstrate that because we can see that K1 is a 0, which is referencing bandwidth, and K3 is a 1. And you could modify this. I have seen on at least one occasion where a customer simply got rid of bandwidth as part of the calculation because they wanted EIGRP to look more like OSPF. And with respect to how OSPF calculates its metric, delay is kind of like a cumulative cost if you think about it. So you could make EIGRP kind of look more like OSPF by simply getting rid of the bandwidth calculation. The reason why bandwidth can be challenging too is because it's the minimum bandwidth along the path, which can be a little bit confusing as well. You may actually inadvertently, so change a value or change values and nothing happens because you're not modifying the appropriate interface along the path that would reference the lowest bandwidth for that particular path. All right. So I guess that's about it. I'm trying to think without going into, because obviously we have variance that we're going to talk about, and we have unequal cost load balancing. But that's going to be reserved for our traffic engineering discussion. We can see in this case, we're still load balancing in one direction because we didn't modify the delay on Ethernet 1.0 on this side, and we're only doing single path routing on the other side. We got a chat message here. Let's see what it says. So if you're going to change a metric in a production environment, is it more preferred to change a bandwidth or delay? I would suggest delay, and again, because delay is on essentially a per hop basis, based on the exit interface. You're going to have a lot more granular control about path selection when you're manipulating delay values than when you're manipulating bandwidth values. And incidentally, the delay value that's on the interface is not usually used in things like QoS and other types of calculations that are considering bandwidth as part of the formula. So oftentimes changing the delay doesn't really affect anything but EIGRP in that environment. So I would definitely suggest delay in that particular case. Because again, you have multiple points along the path that you can manipulate that value. All right. The only other consideration that I would suggest, and we'll see this in the traffic engineering section in more detail, but I'm going to mention it now, is make sure that when you're manipulating metrics on a particular path, that you don't manipulate metrics to the point, or you try to avoid this as much as possible, you don't manipulate metrics to the point where you lose your feasible successors. Okay? Now, in this case, our topology is not really conducive to demonstrating that. So when we do our traffic engineering section, I'll add a few more routers so that we can, take a look at how we can influence path selection by maintaining our feasible successors. Because these are all, this network here is connected to the HQ router. So it's, unless we're doing offsets or doing some sort of metric manipulation, statically, we're not going to be able to change the feasible distance of that path because it's directly connected to the peer router. All right. But you always want to make sure that this second number, if possible, is always less than the primary number of your successor path, because that's what allows you to meet that feasibility condition. Really, really important. Okay. Now, looking at the topology, since this was a little bit of a shorter lesson, do you guys have any additional questions? I know, Ken, you mentioned the K6. We'll talk about that in the next lesson with wide metrics. Do you guys have any other questions about this particular topology, how the numbers are calculated, how we do path manipulation and whatnot? Okay. All right. Well, I guess that's about it for our discussion today. I know it was short. I planned on doing a little bit longer, but I got some stuff that came up that I need to take care of, but I didn't want to postpone. Mike had a question here. Will the written ask you about particular values? Absolutely. Absolutely. You are going to have to know, from a theoretical standpoint, you're going to have to know about all of these values. You're going to have to know the formula. You're going to have to know what components of the formula apply, which ones don't apply, and you'll probably even have to know about how to manipulate metric weights using the metric weights command. So that divide by 10 is definitely a biggie. The other place that you're going to see this as well, I'll mention this before we wrap up here. Let me go into my branch router as an example. And actually, let's do an HQ because we already have HQ configured here. All right. So if I do a show IP EIGRP topology, you can see that the 2.0 whatever network, let me do a show IP interface brief, exclude admin. So this 209 network is not part of EIGRP, or else it would be in the topology database. So we're not running EIGRP on this interface. So I could do a redistribution, router EIGRP 100, and I can do a redistribute connected. And you'll notice that I have an option to specify the seed metric for that redistributed routes, for the redistributed route. Actually, any redistribution process, you could specify a seed metric. The reason I thought of that is because Mike had asked about the 10. Now, when you're redistributing, and we'll see this again a little bit later on, but when you're redistributing into distance vector, you have to specify a seed metric. If you don't specify a seed metric, the routes will not redistribute. So if I just did a redistribute connected and I did a show IP route, I would not see, made a liar out of me. It's probably because it's connected. It's probably because it's connected. Let me do a show IP route 209.165.201.0. Oops. Show IP route. I want to see what it's putting in for the. I'm sure it's doing this because it's connected. /27. Interesting. Show IP route 209.165.201.0.255.255.254. Why is it doing that? It should be 209.165.201.0. There we go. That's what I wanted to see. I don't know why I didn't put the mask in there. But anyway, I wanted to see what it was using for the seed metric. So we can see here that it's putting in a delay of 6,000 microseconds and a bandwidth of 10,000 kilobits per second. Let me try something else real quick. Because let me do a router OSPF1, network 209. 0.0.0, 0.0.0, or 0.255.255, area 0. Show IP OSPF. All right, show IP OSPF route. I just want to make sure that this route is in OSPF. Okay. So now if I go into EIGRP and I say redistribute OSPF 1, and I go look at my branch. Yeah, there we go. So that was the point that I was trying to make, is that when you're redistributing into a distance vector protocol, you have to specify a seed metric. Now, it didn't happen to apply in this case when I had a connected route, but because now I'm injecting this route from another routing process, I have to specify a seed metric. And if I do a show run, section router, we can see that we got the redistribution command. We're redistributing from OSPF 1 into EIGRP, but there's no seed metric, which means the route is coming in with an infinite metric. Now I'm curious, it should show IP EIGRP topology. Yeah, see, it doesn't even show up in this database, but it should be in this database. Show IP EIGRP topology. Yeah, it's not even showing up in this database either. Let's do an all-links and see if it shows up there. No. Okay. So it's the redistribution process is definitely taking place, but it's not inserting the route. Now, there's a couple ways that you can do this. You can actually go into the EIGRP process and you can do default metric, and you can specify the metric, either hops for RIP or waits, or you can actually apply this to the redistribution process. So we did a default dash metric. That's what I meant to say. There. Now we can specify the K1 value. I'll just put 1. K2 value, actually this is K3, the K2 value, which is reliability, the loading, and then finally the MTU of the path. So we can use the default metric command. We can use the default metric command to insert a metric for every route that gets redistributed. Or we could say redistribute OSPF 1 and then specify the seed metric this way. So what I would do in this particular case, when I'm injecting the metric, is I would probably base the metric on what's configured on the interface. So if I do a show interface loopback 0, actually let's just do that, include BW, all right. Actually, let's do include BW and reliability. Okay, so there are the values that we have for that interface. So I could say redistribute OSPF 1 metric, and this is the bandwidth that I would use. This is the delay, but remember the delay in the formula in the redistribution command is in tens of microseconds. Not in microseconds. So I'm going to set a delay of 500. And then as far as the reliability load and MTU, typically that's going to be the maximum reliability, the minimum load, and the standard MTU for the route. All right, so now if I do a show IP EIGRP topology, I should see that route coming in now via redistributed process. That is the feasible distance, which makes sense because that's what we were calculating for the loopback in the loopback 0 that was in EIGRP. And if I go into my branch router, show IP route, EIGRP, I'll see show IP route EIGRP, sorry. I can see that route coming in here as well. It is coming in as an external route, not an internal route. So if I do a show IP route 209.165.201.0, 255.255.255.224, I can see that this is coming in as an external route, and then these are the values that are being used on my local router to include this metric. Because remember, I've got to also include my route to the neighbor on top of whatever the seed metric was that was applied to the route that's being redistributed. Does that make sense? So that's another thing that they may have you do on the exam. They may have you redistribute routes, and then they may specify what kind of seed metric you'd want to that they would want you to have for the route that's being sent into the protocol that's receiving the routes from another protocol. If that makes sense. Okay. All right. So next time we'll talk about the wide metric calculations. We'll look at a named configuration again and how the wide metrics work. And then we're going to get into some traffic engineering. We've got some other pretty important stuff to talk about when it comes to EIGRP. Authentication is really important. We're going to take a look at both IPv4 and IPv6 router authentication. Talk about how we can create these keychains that allow us to do automatic key rotation. So both of these are similar. Named mode configuration we've kind of already done when we did our initial discovery of named mode, but I'm going to show you some additional things here that we can do with named mode. It's kind of more advanced configurations that we can apply. We'll talk about summarization, which is really important, traffic engineering with summarization, and then finally EIGRP over DMVPN, and we'll finish up with stub routing. So all of these topics are what we consider kind of more advanced topics to EIGRP, but the goal is to get you guys to become experts in this protocol so that there's really nothing that you can't accomplish with this particular protocol. So we'll see you guys in the next lesson. Most likely it'll be Tuesday or Wednesday, but because I'm flying back tomorrow night. So I'll send you guys a Slack message and we'll kind of coordinate when the next meeting's going to happen.